proving transition invariant. And recently he's been working a lot on horn clauses, so today we'll get started. Thank you for the invitation and opportunity. Into building automatic verification tools. It might be
his microphone is.
So if you are not, it might be
His microphone is off.
10,000 feet perspective, like what's going on in automation. Okay, so let's start. So it's well known that so from some where some U programs correspond to recursive equations and proving properties of programs actually correspond to solving equations, so the original equations, or something derived from that. And was that?
Okay, so this goes through several decades, and sort of originally, so there was a lot of work on set constraints, and so there was a work on point analysis using set constraint solving, and so there were different solving backends. So there were so there was graph reachability. So then there was BDDs and SAT, and so recently, so one of the data log solvers, DUP, actually goes and chases explicitly the tuples. Yeah, they say BDDs are for some particular problems are not that useful. And so so what we're looking at here is that actually if you say okay, the magic word SMT, yeah, so then so the constraints you're writing, so you can put the literals over background theory, and sort of things get even more expressive, and you can present more sophisticated questions about programs. And another actually sort of piece of insight that I owe to Muli is that he said that, okay, early days people try to encode reasoning about data in your program into function symbols in your data log. Yeah, and these days we just use SMT. So we mostly use sort of this Horn or data log style clauses to represent sort of control related aspects, and sort of all the program data reasoning is actually taken care of by the background theories. Okay, so first I will show you so a few proof rules for linear properties, so for universal properties, saying, okay, so in all program computation, something happens or something does not happen. And then we will look at the existentials, both in the properties and in the clauses that we need to solve. So we start sort of with a brief sort of reminder how we might view a program. So we have a bunch of variables that are in scope. And this is a flat program, sort of no fancy programming language constructs to modularize. So you have a description of initial states. You have a transition relation, sort of called step, tells you essentially how you update memory in one step, you execute in one instruction. And say you have some safety specification saying that you'll never leave the set of safe states, or the termination specification could be that starting from init, you always stop at some point eventually. Okay, so and one of the rules for proving termination of transition systems is that sort of forward execution. So where you're looking at program executions from this set perspective. So it's well known that reasoning about sequences or trees, all these things, is very sophisticated. And so what is done in verification is, so the first thing we do, so we go away from reasoning about traces to reasoning about sets. Yeah, and so we can represent sets using assertions, and implication checking, all these things come in quite handy. So with the reasoning by induction over the number of steps it takes to reach a state, and so in the verification induction hypothesis is called an invariant. So we're looking for an invariant. This is existentially quantified. So usually we represent invariants as assertions. And so there are two conditions on the invariant. So it holds initially, so the first implication, and the second implication. So it holds after one step if you assume the invariant. So there is not much going on here except for two facts. So first, so here we quantify existentially over sets and relations. So an invariant is a set of states, and we're going to quantify over binary relations and so on. So there is a little bit color coding going on. So stuff that comes from program source is black. And everything that we quantify existentially, so everything that we need to infer, is in blue. this a little bit. And the second point I would like to make here, if you look at the shape of the equations, so what we notice quickly, there is no disjunction on the right-hand side. Yeah? So which means, so if you strip away implication, so and look at the implications as a set of literals joined by disjunction, so we have at most one positive literal. Yeah, and this is so-called language of Horn clauses. Okay. So this is the specification of an invariant. An invariant is supposed to be useful, so in the sense that it's supposed to be either strong enough to prove the safety condition, or it's supposed to be restrictive enough such that when you basically restrict your transition relation to what's reachable or reasonable over approximation, then the resulting relation is well-founded. This way we can prove termination. So this is one way to prove termination. Alternatively, sometimes it comes in quite useful, is we can compile away the request for well-foundedness, so which usually is dealt with using some ranking functions by reasoning about transitive closure of the relation that we want to prove well-founded. We say, okay, so the relation is there, and every time I'm doing sort of one-step extension, basically rel plus, so it's all captured in so-called transition invariant, and here, so we allow to cover the transition invariant with the union ranking functions if you want to prove termination. Okay, so this is pretty much it. So from the sort of basic settings, so we have existential quantification over sets and relations. So we have implications connecting these existentially quantified entities, and so they're wired together using bits and pieces of the program. So the equations we are writing are in the form of Horn clauses. And so to deal with eventualities, we allow second-order predicates well-founded or disjunctively well-founded. So if you look at something more interesting, so programs with procedures, so we can say, okay, so if we have initial states, step represents now the interprocedural part of the transition relation. So basically, if you're just doing something like I++ or if then else, this is within step. And so what we are adding is two relations, call for the parameter passing from caller to callee. Yeah, so basically the same. So you have some actuals and you put them into the formals, and you have the return value passing, so usually from the return variable sort of back to the scope of the caller. So this is CFL reachability in 4 equations. So this is Horvitz, Sagiv, reps 95. So I wonder if it's recognizable. First time. So basically, and for those who are familiar with the paper, so in that paper, so there's a summary relation and the path edge relation. So for the notational convenience, so I'm calling summary the union of both. And so what's going on here is that we want to bridge over calls. So using these so-called summaries, which basically tell you, okay, with this input, I'm going to produce that output. So we start summarization in the beginning of, say, main, and saying, okay, so if I'm called from the beginning of main and don't do any steps, so this is how far I get, this summary v0, v0. And then so we extend in the summary, and this is the sort of path edge style extension. So when we execute intra-procedural statements, so summary keeps growing, so it goes from v0, v1 to v2. And so every time we do a call, we start summary computation in the callee. So essentially v0 and v1 is in the in scope of the caller, and call relation brings us from the scope of the caller to the callee. So v2 is sitting inside the callee. Yeah, and summary v2 is essentially something very similar here. So is the pair of states that are reachable by starting somewhere from the beginning of main and coming to this particular call site. And so what we can also do, once we have reached the call and we have actually a summary relation for that call, so what we can do, we can jump over the call site and then get back to the namespace of the caller. And so in this way, we actually, in one fell swoop, we go sort of over all these calls and returns everything underneath back to the same level of recursion. So we jump from v0 to v4. And probably some of you are going to say, oh, but where's the frame rule? And so essentially, so if you want to be more faithful, you can say, so the locals of the caller, so something referred to by v1 and v4, actually are not supposed to change, you just add inequality. Okay, so this is summarization for equations. So summaries are supposed to be useful. So summaries are useful if they allow us to prove that everything that's reachable is safe. And so this last condition requires that it's not possible to go on forever and push on the stack. So what it means is that actually this way we can require that the program does not go on forever sort of with the increase in stack breadth. So basically there is no non-termination due to recursion. Yeah, and sort of in a similar way we can require that there is no non-termination due to sort of getting stuck in a loop. Okay, so and trust me, sort of this looks very simple, but if you try to build a termination checker for programs with procedures and recursion, so it gets a pretty serious nightmare. Okay, so one point I would like to make here about the shape of the equations. Yeah. So in contrast to the equations for transition systems, what we observe here is that, okay, so some of the equations have one unknown, like we had, so invariance and step implies invariance, and some of the equations now have two unknowns. Yeah. So basically you're combining the calling context and the summary when you're jumping across the a call. So what it means is that actually if we unfold these equations, so for transition systems, unfolding gives us a sequence, and that's what we actually usually call a counterexample. So it's a path. And for programs with procedures, counterexamples are sort of properly nested trees. Yeah, and this is what you actually obtain by unfolding this kind of equations. So you get a resolution tree. And beyond that, so actually there is not much conceptual difference between transition systems and programs with recursion. So if you look at multi-threaded programs, and here again I'm taking a very simplistic perspective. So what's going on? So we all know that there are all these various compositional and non-compositional local global rules for proving multi-threaded programs, and sort of let's look at them from the very simplistic constraint-based perspective. So say our program uses shared memory, so G, variable G is shared, L1 and L2 are the locals, so from thread 1 and thread 2. So I'm using V as the vector of all program variables, yeah, which is kind of useful for some technical reasons. And so all the assertions I'm writing are actually over all the program variables. So again, we have initial state saying, okay, sort of global is it has some value, and say both threads are sitting at their initial locations. There are some global safety specifications. So for example, we can talk about mutual exclusion, so we actually relate locals, so the program counters of different threads. And for the transition relation, say, okay, we have step 1 for one thread and step 2 for another thread. And since I'm referring to all the variables in scope of an assertion, I implicitly assuming that step 1 entails that the locals of the second thread do not change. So basically, here's a little conjunct saying L2 is equal to L prime, and sort of symmetrically for the other thread. Okay, so this is a very simple, but actually very useful model. And sort of this is the so-called relay guarantee proof rule for safety. So the idea is that you pick an invariant for each of the program threads. This is you're saying, okay, there exists an invariant 1 and invariant 2. Okay, and so you want to be compositional, and compositional here essentially means that in one equation you're not referring to transition relations of more than one thread. Okay, so and so to ensure compositionality, you're saying that, okay, I'm going to summarize the effect of the other thread, and sort of this summary I'm going to call an environment assumption. And so here's a existential quantification of binary relations inf1 and inf2. And so now we're going to wire them together. So the first equation says, okay, so invariant of the first thread holds initially, so that's okay. So the second one is getting more interesting. So the first part up to here essentially says that the invariant of the first thread is preserved under the local steps of the first thread. Yeah? So invariant 1, step 1, implies invariant 1 prime. The second part of this equation says that every time the first thread makes a move, starting from somewhere that's perceived to be reachable, some over-approximation of this move, of this going from V to V prime, is actually recorded in the environment that is shipped to the second thread. Okay? And so what we also need to do, we need to account for transitions from the other guy. And so that's what we're doing. So we're saying, okay, so the invariant of the first thread is actually preserved by whatever all the rest is doing. And so the other thread supplies pairs of states for environment 1, and so we have preservation of the invariants. So this is a very abstract take on relay guarantee for safety, and so this is what we implemented. This is what's sitting in the thread verifier. So there is a somewhat other well-known, very prominent approach to compositional verification. It's called Avicii-Gris proof rule. And it actually turns out, if you sort of step back a little, you can derive Avicii-Gris proof rule by applying one resolution step on the relay guarantee proof rule. So essentially what we can do is say, oh, there is this equation that's populating environment of the second thread, and there's this equation saying that invariant of the second thread is preserved under the steps of the first thread. So what we can do, we can resolve away this guy. Yeah, so basically we plug in all this into here. Apply resolution. So okay, env2 is defined by the conjunction. So we plug in here, and now, so for those who know Avicii-Gris, actually start seeing that actually, wow, you get it in one step. So this is what we obtain. So the Avicii-Gris says, I have my preservation regarding the local invariant. I have the preservation against the actual steps, not the relays, but the actual steps of the other thread. And when I'm checking this non-interference condition, actually I'm allowed to assume the invariant of the other thread. And so from somewhat philosophical perspective, one could say that a relay guarantee introduces a lemma, so this relay or guarantee assumption. And so if you go for Avicii-Gris, you're just saying, okay, so I will fast forward and do not use the lemma. And it turns out that, okay, so we are using both in our benchmarks, and it's, sort of the experience shows that actually there's no clear winner. So what is better, relay guarantee or Avicii-Gris? So, and sort of some sort of a little bit of feeling is that actually if there's not much interaction, then relay guarantee sort of seems to lead to a shorter running time, because you can over-approximate the effect in the relay or guarantee, sort of, and store it as a lemma. And then sort of here, instead of actually checking implication against the sort of the detailed transition relation, you check an implication using just some over-approximation. But if there is an intricate interaction, actually sort of Avicii-Gris tend to work a little bit better. Okay, so and sort of the third trick for dealing with multi-threading is so-called thread modular proof rule. And the idea is that you're only allowing local assertions. What it means is that our invariants are going to talk only about the variables in scope of the individual threads, so which means inf1 now talks only about G and L1. And our environment is going to talk only about the globals. So the corresponding constraints are actually quite straightforward. So we just change the variables that are in scope. And when we populate the invariant, since locals occurring here don't show up in the head of the implication, so then implicitly existentially quantified, so get a projection on the global scope. So there is one interesting point one can make when looking at the proof rules for multi-threaded programs. So actually, if you write down constraints and ship them to the verifier, then the verifier is actually sort of, is not going to be able to make a difference if these constraints are coming from, say, verification conditions for programs with procedures or multi-threaded programs or something else. Because so once you have more than one unknown in the body, sort of, yeah, so that's pretty much it. And so it's well known that if you allow two unknowns in the body, so then you can reduce everything to this form. It's like once you admit 3 variables per inequality, so you can represent all linear programs in this way. Okay, so that was concurrency. And so what I don't want to show you is that sort of there is, if you care about a different way to modularize your programs using high-order procedures, actually there's a very neat trick to do that. It's called refinement type systems. Essentially, there's a pre and post conditions, so a similar way you use them for procedural programs, for imperative ones, but you can sort of apply the same trick for for higher order, and every time you pass a procedure as a parameter, so in your higher order program, essentially what you're asking is something very similar to the conditions that when we call the procedure. So you have contra and covariance on the pre and post. So that's pretty much it. So and so the resulting constraints turn out to be again Horn clauses. So you can essentially have one solver that takes sort of constraints generated from higher order, from timed automata, from C, Pascal, whatever. Okay, so that was pretty much the, yeah? Yeah. Yeah, that was actually our first front end. So the liquid type constraints. And it's pretty neat because it's not only compiling away sort of the refinement type system, compiling away the high order stuff, it also take care of algebraic data types, all these kinds of things, because essentially all these things are functions. Yeah, so it gets really smooth. Of course, so for if you take constraints generated through a refinement type systems, you are pretty much immediately losing completeness, because so this constraint generation is already sort of not very much context sensitive, but who cares? Okay. Excellent question. This was one of the reasons why I said that we're going to keep all the variables that are present in the program in the vector V. So in principle, sort of this constraint system doesn't require the invariants to be local. Yeah, and so what you can do, you can go for the localized version. So without auxiliary variables, so where you write in GL1 and GL2 here. So if your constraint solving fails, so basically you get a derivation where you're saying, oh, I cannot solve this recursion-free derivation, then you're saying, oh, now I actually know for sure that there is no Wiki-Greece sort of local proof. And then, so you're saying, okay, all bets are off, I'm allowing all variables in scope. And actually, so what happens in our solver, so you can bias the solving to go for local proofs, and if it realizes that so there is no actual local proof, then it goes for arbitrary assertions. And basically, once you have relations between locals from different scopes, you can actually see them indirectly as a definition for auxiliary variables. It's up to you, so it's a program counter variable.
You just have one.
Yeah, it's just a local variable. Yeah, but again, so you can always give heuristics to the solver saying that, okay. Okay, that was essentially a little introduction to quantifier-free fragments, which is very useful if you want to prove universal properties of programs. And so what if we want to do something that requires a little bit of alternation? And sort of, so before I move to yes, so this is the Blackbird picture. So this is essentially one possibility how to solve the quantifier-free recursive clauses. Essentially, these are 7 inference rules. And so what they do is so it's actually a very simple and natural way, and so everybody else is doing it this way. So you have recursive equations. So to recursion is difficult. So what you do, you say, okay, so actually recursion is just a syntactic way to represent infinitely many recursion-free equations. Yeah. So and you grab some finite subset of the recursion-free ones, you solve them because there is no recursion, so you can do things like something really similar to Gaussian elimination. Yeah, but it's all modular theories and sort of SMT. So and then so what you do is so you take the proofs that some chunk of recursion-free equations has a solution, and then sort of you toss these proofs in the air and sort of grab them and try to spawn an abstract domain, and you hope that in this abstract domain, so these proofs for bounded unfolding will generalize to a proof for unbounded unfolding. And if it doesn't generalize, then okay, so which means there's a even deeper unfolding, and then you play this game. Is it really not solvable, or is it just because of the abstraction function? And then so you unfold deeper, and essentially play this, the same game. So, and these are just the rules representing unfoldings. So another point I'd like to make, so here, so I'm mostly focusing on the sort of constraint generation part, not on the constraint solving. Sort of trust me, sort of there is a background solver for all these bells and whistles with well-foundedness, disjunctive well-foundedness, quantifiers, and so on. Sort of, if you're interested, ask me after the talk, but I don't want to clutter the presentation with all these nested details. But essentially, sort of, there is no magic at the end. So at the end, so what you rely on is decidable theories and proof generation and generalizations of proofs, sort of the standard stuff. Okay, so now to quantification. So there are many different reasons why you would like to have existential quantification or universal quantification in your equations. For example, you want to deal with branching time properties. You want to do synthesis where there's interaction between the environment and the player. So there are many other reasons. So the existential quantification is very useful. For example, you might want to say, oh, there exists a bound such that blah, blah, blah. So you just existentially quantify over the expression, and you think of this expression as a witness as a Skolem witness. Okay, so we are first going to look at the for all exist quantify alternation. We assume that neither body nor head actually has further quantifiers. And if it does, so we can always lift them up. So the interesting aspect here is that when you have this for all exist quantifier alternation and recursion in your equations, essentially, so you have infinitely many quantifier alternations, because you unfold the recursion, every time you unfold this for all exist, for all exist. So things like to play LTL games sort of so get within reach to some extent. Okay, so for all exist clauses. So one sort of a classic application is proving branching time properties. So and actually, luckily, there are already proof systems for CTL. Essentially, one perspective on the proof system is a constraint generation mechanism that says, okay, so I'm going to compile away the sort of temporal aspects into first-order aspects, and this one is due to Kesten and Pnueli. So we're going to look at two examples, and so you get the idea how it works. So if you want to prove an individuality property, something, EF or some Q holes, for example, there exists a path that, I don't know, I write something to the hard disk. So the, this formula has only one path quantifier. This exists, so we can take it as is directly and start generating constraints. And sort of the idea how to go away from temporal to first order is actually quite simple. So we want to reach the assertion Q on some path. So what it means is that we need to get there through some set of states, and this set of states we're going to call an invariant. Yeah. So and another aspect is that actually we really want to get there. So what it means is that actually we want to have some well-founded argument or termination argument actually pushing us towards Q. And this is what we're writing down. We're saying there exists a set of states towards Q. So doesn't matter where we start in it. So we are on the right track. So if we're on the right track, but not yet at the destination, so okay, so there is a way to move on, get closer. So we're getting back on track. And so there is a well-founded relation that says, okay, every time we make a step, actually, so we're getting closer to some limit. So since we cannot go on forever, it means because of the round being well-founded, eventually we're going to hit Q.
It's not Horn.
This is not Horn.
No.
Very good question. So we have negation, but only over the black stuff. And black stuff is the stuff coming from the program. It's a formula in the background theory. So it doesn't impose any trouble. So what we do not want is non-Horn with respect to the blue stuff. Okay, so this is sort of Hornish, and sort of fits to the format accepted by our solver. So if we have a more sophisticated property, so where we have actually nesting of the path quantifier. So the trick is that you can actually decompose your big sophisticated formula into a conjunction of small formulas actually that do not have nesting of path quantifiers, only one path quantifier on the top, and that's it. And how you do it is by essentially rely on the fact that a CTL formula represents a set of states on which it's actually it's true. So what we're going to do something that what people in SMT call purification. So essentially you throwing away the nested subformula and representing it, taking a set of states that it represents. So we quantify over some set of the middle states, and then we're requiring that sort of the topmost formula is actually holds over our system with respect to the middle, instead of the actual sort of temporal representation of what middle is. And then we're saying, okay, so whenever you start in the middle, then the nested temporal formula is supposed to hold. And so you can imagine that if you have a sort of your syntax tree of the CTL formula with the nodes being path quantifiers, then you just take a subtree one at a time, replace it by a set of states, and generate a new verification condition with a simpler CTL formula. Okay, so this way you can flatten everything to a bunch of existentials over the unknown decomposition and a bunch of simple sort of so-called basic path formulas. And then for those basic path formulas, you can actually start generating constraints. This is how it looks like. So for the EF, this is what we have already seen. No, this is EG. So we want that there exists a path where we always stay in the middle. So again, there's a set of states along that path, inf1. Every time we are inf1, we are supposed to be in the middle, and so we are supposed to be able to carry on and come back. And then what also happens is that due to the second question, so there must be a set of states that actually gives us a path that sees P until Q shows up. So which means we are on a path that has where all sets of this path are described by invariant 2. So whenever we are not at the destination, so we satisfy P, we get back on track, and so there's a well-foundedness condition. So what it means is that in inf2, we stay in P, and at some point we hit Q. Okay, so and again, this is Horn if you consider the shape of the blue stuff. And sort of the ultimate level of excitement you can get with this quantified alternation in temporal is solving games where you have on one side the system and the other side the player, and sort of every time doesn't matter how the system makes a move, sort of the player has, so there exists a way to counteract and sort of reach some objective. So one of those games is so apparently very popular in the sort of today's synthesis community, so-called Cinderella stepmother game. And so it goes like this. You have 5 bottles, and they are arranged in a circle. So and it's important, sort of the circle arrangement is very important. And so what happens is that at every round, stepmother takes a jar full of water and somehow spreads the water across the bottles somehow. And then Cinderella comes in and empties a pair of adjacent bottles. So that's why sort of arrangement in the circle is important. So 1 and 2 is okay, but 1 and 3 is not okay. So then stepmother comes in and pours even more water, so the jar gets refilled. And Cinderella wins if there is no overflow, basically sort of there is no water on the floor. And sort of the nasty stepmother wins if she manages to actually to make some of the bottles to overflow. So it's a big mess. Okay, so here's the view on this game from the perspective of assertions and equations. So we have state variables are actually the current amount of water in each of the bottles. So we have the variables from V1 to V5. So B and J are actually the capacities of each of the bottles and the jar. And so here they look like symbolic constants. So our solver is not capable of dealing with the symbolic constants. Actually, it's a very sophisticated question in games, sort of how to find a strategy that actually is parametric in J and B. So we solve for particular values in the experiments. So initial condition is that all the bottles are empty. So V1 through V5 is all 0. Cinderella's move is pick a pair of adjacent bottles like 1, 2, or 2, 3, or 5, 1, empty them and sort of say that nothing else changes. And what stepmother is doing is she's saying, okay, so I'm going to top up. so the amount of water in each of the bottles is not decreasing. And actually in the delta across all the bottles, so the after topping up minus what was there before is actually equal to the jar capacity. And so the overflow condition is that some of the, at least one of the bottles is above the capacity, capital B. So from the perspective of stepmother, yeah, so winning the game means eventually reaching the set of states described as overflow. Again, so what does it mean to get there? So you get on the right path and you keep going until you hit it. So let's call the set of states traversed by the stepmother a winning region. So we want that initially, doesn't matter where we start, so we are winning. So if we didn't win yet, so if there is no overflow yet, then it doesn't matter what Cinderella is doing. So remember that V and V prime are implicitly universally quantified from here. Doesn't matter what Cinderella is doing, so it doesn't matter how she is emptying some of the bottles. So it's possible for stepmother to counteract and get back to the winning region. Okay? And again, so requiring that sort of in total, Cinderella step and stepmother step, so this entire round, so when we start from V and go back to the winning region at V prime, so this relation is supposed to be well-founded. What it means is that with this alternation, so for all Cindy exists stepmother, for all Cindy exists stepmother, sort of in this tree, so there is no path on which we actually go on forever without hitting overflow. Okay, and so you ship this constraint to the solver, so wait a little bit, if you're lucky, then so you get the strategy for stepmother. And you can read off the strategy for the stepmother by essentially looking at the witness for this existential quantify, which is going to tell you how to actually top up the bottles. And so you can imagine that sort of this was a particular eventuality, reachability objective, and you can spin it to full-blown LTL objectives if you wish so. Okay, inference of transactions. So transactions are sort of another interesting example that we're looking at where existential quantifications comes in very handy. I would like to skip all the details and just give you the reason why existential quantification. So transactions is usually very tightly concerned with the notion of commutativity. And commutativity essentially says that, okay, so if you have two relations A and B, and composition AB is included in composition BA. And relational composition means existential quantification. So, and when you're saying that AB is included in the composition BA, so there is existential quantification due to the existence of the middle state, and sort of then the entire story rolls out. And then you can sort of write more equations describing, okay, so what is a transaction and non-interference and commutativity and so on. I'm going to skip over this and get to the universal quantification. So in principle, sort of existentials and universals, so one is the dual of the other, so you can do some magic tricks, but sort of practically it's useful to look at them as sort of as a syntactic entity that deserves attention or sort of by itself. So think of the universal quantification as the quantification that is trapped inside the body. Yeah? So which is different from the universal quantification that is sort of quantifies across the entire clause. Yes, and you can say, oh, since this guy under negation, so essentially it's an existential, yeah, but sitting in the body. So one interesting application for this universal, and actually, I don't think so there is an interesting other one, so but maybe someone can point out, is inference of universally quantified invariance. And so you can always imagine, so you have your program that writes into memory at some unbounded number of locations, and you want to talk about all those locations, but you don't want to, or you cannot actually name each of them, yeah, because then the formula will become of infinite size. And so if you look at the literature, actually there are quite a few methods for the inference of quantified invariance. And so if you abstract a little bit away from the concrete solving details, there's a trend. So first of all, there's something about quantification template, there's instantiation, then actually the actual solving with abstract domains and stuff. So if you look somewhat more concretely, so what is quantification template? Essentially, you are picking how many quantifiers you allow in your invariant. So usually it's one. Yeah, but sometimes if you want properties like sortedness, so it's two. So you're saying, okay, for all I and j being positions in the array, if there are one is less than the other, then array values at so the respective positions are also ordered. So you pick how many quantifiers you allow in your environment. Then the magic step is actually quantify instantiation. Yeah, so this is actually where all the magic, or some like 30% of the magic goes into. So essentially, a universally quantified assertion is like an oracle. You can ask it a question, and it'll give you an answer. And asking a question means giving a quantified instance, and getting an answer is basically getting back the instantiated formula. And for obvious reasons, there's only so many quantified instantiations we can actually make use of. Yeah. The trick is actually to pick the instantiations, this E1 through the EK for the quantifier. And once you are done with the instantiation, once you supply the instances, there is somewhat the science and art of the actual invariance inference. And so usually it's done in abstract domains because most of the time, there is an interest in obtaining quantified invariants that are somewhat of this shape. So you have a guard that restricts the range of the quantifier, and you have a property that essentially pokes into the array at the quantifier locations and relate them to everything else in the program. And here the tricky part is that since guard appears under negation, then actually to be sound during your inference, you need to under-approximate the guard, where it's kind of well known that, okay, most of the stuff we over-approximate and under-approximations are really, really tricky. Okay, this is the standard flow of quantified inference, and so what we would like to do is get rid a little bit of the magic. So basically, we would like to get rid of this and this part. So essentially, from the user perspective, or as some people call it, from the verification engineer perspective, just pick the number of quantifiers, everything else is supposed to be automatic or not successful. So here's the idea. So we write down the quantified assertions as is. And the actual invariant is unknown, but we just boldly go ahead and write down the clauses. And then the question is, okay, so this for all P, so we can strip it away, but how to instantiate the P inside the body of the clause? Actually, second and third clause. And that's what I just said. And the idea is actually surprisingly simple and maybe a little bit frustrating. So if you look through the literature, so there is one quantified instantiation heuristic. The blackboard? Yes, now there was a big disclaimer saying that I would like not to dive into solving, but the general scheme is unfold to a bound, get the solution up to a bound, and try to generalize. I can give you tons of details tonight about solving. The crisp abstract explanation is unfold to a bound, solve the recursion-free clauses, and generalize from that proof. Okay. So in this heuristic is essentially what is known in automated deduction, the local instantiation. So essentially what you're doing, you're looking at the positions at which you are reading into an array in your formula. You collect all those, you do a little bit of closure computation due to array updates, and so this way you get a set of quantifiers. So it works very well for transition systems, so for while programs, and it doesn't work that well for procedural programs because there is no way to join quantify information from the calling context and the summary. And so I will tell you how to avoid that thing later. But first, let's look at the vanilla stuff. So for example, for this formula, so what we're going to do, we're going to say, oh, I'm reading into array A prime at position Q, here in the head. That's why in the set of instances for A prime, so Q is going to show up. Since A prime is obtained from A, so all the instances for A prime are going to be used for the instances for Q, for A. So this way what we obtain is that, okay, so we're going to instantiate this P with Q. So once we did the instantiation, so we get quantifier alternation-free clauses, we just use the standard sort of solver described on the blackboard, so to solve that stuff. Okay, and so that's pretty much what I wanted to say. And sort of there is a lot of there's a lot going on for the solving perspective, and essentially, as I said, unfolding. And unfolding actually means doing resolution. And so once you do resolution, you compile away all the existentially quantified stuff, so you get an assertion in the background theory. So then you prove unsatisfiability of that assertion, and from the proof of unsatisfiability, you can actually decorate all the rest in your resolution tree. And so there are some doubts if when you go from program verification question to this constraint solving question, sort of what is lost in translation. And sort of the answer is, at least so far from my perspective and sort of a few other people like Ken or Nikolaj, is that actually not more than so when you go from C through say a CIL frontend or from Boogie frontend to your verification conditions sort of in the sort of standard way for shaping things. And so that's pretty much it. Thank you very much.
Been a classical problem in database theory, and basically it's been considered a barrier to handle all kind of things. So if you think that you can handle in practice this kind of thing, that may have a significant database application. Because there are many examples. That's what we need to solve. We need to solve the essential relations you have constraints that their own constraints. Find a person in it. And if you solve various problems around them, it all ends up in solving this problem. It's fairly big. No, not really vulnerable. They're doing it not to the level of the databases, but to the level of what's called schema level reasoning.
And what would you like to involve with these constraints? Could you give an example?
And so many kind of natural level of constraints are actually naturally written as one clause in the quantified horn. For example, if you want to have a relation, and you want to say if you have like the one relation that has all the students, and then you have relation of students taking classes. So you want to make sure every student that take classes appears somewhere in the big student relation. Right? That's an existential constraint. There is a tuple in the student relation that has the name of this particular student in the course relation. So if you want to do reasoning about this kind of constraints, then it's essentially reasoning about this kind of workload.
Yeah, but then this would be a reasoning about the program that actually populates the database.
No, you don't need to. You can populate something and just get a set of foreign constraints.
Thank you.
More questions? I'm not entirely sure how you use the fact that they are Horn clauses, but there is this slight, not generalization, but there's a slightly general class of formulas, the hereditary Harrop formulas. Does your approach and can you make use of them as well?
It's on my list of things to look at on Wikipedia.
Because it's the basis for higher order logic and all the theorem proving stuff that has been going on.
So I tried a few times to read the definitions, but on Wikipedia it's so condensed that I just couldn't understand it.
Okay.
But yeah, so thanks for pointing it out. So, but sort of to the first part of the non-question part, actually, what is the significance of clauses being horned in this entire process? So since the clauses are horned, then actually you take them, and from them you can get a multivariate function. So basically, one step updates sort of all the relations. And the interesting connection is that this fixed point of this function is the strongest solution to the clauses. And then you can imagine that, okay, so if you do over-approximation, that over-approximations of the least fixed point are going to be some solutions. This is basically the basis for these iterative solving algorithms where you just some way pick an abstract domain, and so then you do abstract interpretation using this function. And if the clauses are not horned, so basically there are tricks you can play, but you lose this nice function.
So is it like the backchaining sort of but on all possibilities at once. Kind of.
Yeah, yeah. So you do all these things symbolically. Yeah?
Thanks.
More questions? So let's take Andrey again. Okay, there is half an hour break now.